Good morning, everyone. I'm Wenliang Zhong, algorithm engineer from Alibaba Group. I will present our stock constraint recommendation in Tmall. This is the genre with Professor Rong, Cheng, and a few of my colleagues. Here is the outline. First, I will introduce the background, followed by problem formulation and optimization methods. Then we extend our model to online algorithm. Finally, we will present our experimental result on synthetic data and real data sets, followed by the conclusion and future work. What is Tmall? Tmall is an e-commerce website. It is one of the major business users of Alibaba Group. It is the largest third-party platform for brands and retails in China. We have more than 300 million annual active users with a very high GMV. Say, for example, in the Double 11 day promotions, we gained $9.2 billion US. And this is a cat because the Tmall, mall is the pronunciation of mall is the same as cat. So this is our mascot. Okay, a cat. As a bit e-commerce website, we have developed a lot of recommender systems on Tmall.com. Some of them are personalized, while the others are not personalized. For the personalized, that means we recommend items based on your interests or your historical behavior in the past few months or years. And the recommender system also includes real-time or offline ones. For the real-time, that means we check your steps in real time and recommend the items instantly. For the offline, because due to some efficiency issues or some special business purpose, we also perform some offline recommendation. That means we store the recommendation results in a table, then recommend items by simply looking up those tables. And here is what I want to talk today. It is item-to-item recommendation. It's non-personalized and offline. Here is the example. This page is called a detail page of some item, and we want to recommend items on the right-hand side. This position is called also view. Well, we found that most recommender systems are optimized for click-through rates, and no existing work in e-commerce have considered the inventory size. So it's possible that out-of-stock recommendation occurs, which lead to bad user experience and reduce the impact of recommendation. Based on this motivation, we have developed a stock-aware recommendation system. Before introducing this system, let me introduce the notations. We consider n items with price P and inventory size X. Fi is the expected float, that is the average number of visits to the detail page of item I. And Ri is the expected conversions rate, which means the probability to purchase item I when you visiting the page. And we also have constant C matches C, which is item-to-item CTR matches, where Cij denotes the CTR of displaying item J when visiting the detail page of item I. And we want to learn the recommendation matrix A, where Aij represents the chance to recommend item J when we visiting item I. So based on this notation, we can first write down the number of visiting item I. So it consists of two parts. The first part is the expected traffic flow from any other resources. Say, for example, the web search or the advertisement. And the right-hand side is the traffic flows that induced by this recommender system. So we have the CTR, the recommender matches, and F is all the other items. So we can it will induce some traffic to item I. And based on this, we can calculate the sales volumes of item I. So this is the traffic flow, and this is the conversions rate. So this part is the max number of sales volume we can reach of item I. It's limited by the stock. There is the inventory size Si. So we minimize here. Then it's necessary to come to the total sales revenue. This is the sales volume, and this is the price. We sum over n products, and we get the sales revenue. Because the conversions rate R and the traffic F are estimated from historical data, they can be noisy or unreliable. So we need some regulations on each row of A, which is entropy regulation. Then finally, we get this object to optimize. We want to maximize the sales revenue together with a regulation term with a set of constraints. These constraints are used to ensure that A has the valid probability meaning. As can be seen, this objective has n square variables with non-smooth function because due to this mean and a number of constraints. So it's inefficient to directly optimize this objective. To overcome this obstacle, we introduce the duality of this problem. Well, first, based on this simple observation that we can get rid of the discrete mean operator with a continuous variable kappa. Then, using this observation, we can replace all the minimizations, all the mean operators in the objective, then take a derivative of variable A, then we can get the dual problem as this one. The good news is this problem is smooth, and we only have n variables at this moment because this kappa corresponding to only one item. Okay, once we get the solution A, we can recover solution kappa. We can recover A using this formula. All are constants, and you said Z is a normalization factor. Then we employ the accelerated gradient descent method to solve the dual objective. First step, we compute the diagonal Hessian matrix, which can accelerate the algorithm a little bit fast. Then during the loop, we first, well, overall this is just a very standard accelerated gradient method, so I talk about it in a little bit fast. So it's a combination of two estimated solution kappa, and then we compute the solution A using A for the gradient G, and then finally we perform projected gradient descent. This is a standard projected gradient descent with proper step size eta. And this is the trick to accelerate the gradient method. It's fairly standard. And as you can see from this algorithm, the main complexity is computing of matrix A, which is equivalent to the number of non-zero elements of C. And it takes 1 over square root of epsilon iterations to achieve epsilon accurate solution. So in general, it needs 100 to 200 iterations. This is the algorithm of batch part. And because in some cases the traffic F and the noise and the conversions rate R can be quite noisy. Say, for example, due to the big promotion, we attract a lot of new customers, and also because of some coupon or discounts, the conversion rate improve. So we try to try to perform this update using in online style. That is, we recalculate the price, stock, conversion rate, and the traffic, and see in its interval. We divide the whole learning procedure into T intervals. Okay, so this is the online objective. Everything are the same except that we have T intervals, and these constants are changed along with T. And to optimize the online objective, at the beginning of the T's interval, we know the stock and price because our system record these numbers. However, for the CTR and the conversion rate and the traffic flow, it's undetermined because it's not happening at this moment. So we use the number from last iteration to replace this one. So head R, head C means an estimation, not the true number. Then we update the solution using abstract gradient descent, which is standard in the literature. That is, well, we perform projected gradient descents on auxiliary solution head kappa with the estimated gradient. So this involves some estimated number, that is head C, head R, or head F. And at the end of the T's interval, we update the kappa again using the true gradient. As at the end, we know this ground truth. We can use this ground truth to calibrate this gradient. Then we perform gradient descent again. So this is called online optimization. Okay. Now let's come to the experimental session. We perform experiments first on synthetic data set. We generate these numbers randomly, and we compare the baseline method, CTR first approach, and the CTR multiplied CVR approach. And at the testing stage, we add noise to the conversion rate and expected traffic. And we perform the simulation of a sequence of user visits. This we try to receive a lot of users one by one. And only the online approach can update its model during the testing phase. And here is the results on synthetic data set. The x-axis is the number of impressions or the number of user visits. And the y-axis are the sales revenue on the upper line. And for the bottom line, it's out of stock view. And as can be seen, the sales revenue gained by the online approach is much better than the rest. And also, it has the lowest out of stock views. And the second best method is our batch method, which is the green line. And it also has a lower out of stock view than CTR first approach or CTR multiply CVR approach. Okay, then we come to the experiments in real data set, which is we test our algorithm on the real traffic on Tmall.com. In training phase, we use over 100 million items from more than 10 categories. Here, category means computer or clothes or some furnitures or something like that. And the traffic flow F is estimated based on the data sets in the past week. And the CTR are estimated by a hybrid machine learning approaches on the data collected in the past month. And roughly speaking, we have 10 to the power of a non-zero elements. And beta is turned on small subset. and we retrain this model every day. And during the testing, we report the results for every day. There is one figure for one day, and we report results from a whole week because probably the situation at the VN can be different from the daily working days. And A/B tests are performed on two groups of over 10 million users. That is, the division is based on the user ID. And there are at least 1 million impressions behind per dot in the figure. I will show you here. Due to the space limitation, I just show results on 3 days. For more results, you can read our paper or come to our poster tonight. And the first line is CTR, and the bottom line is the sales revenue. You can see that we improved the sales revenue on 16%, but with a lower CTR as expected by 14%. We also report the results across different categories. And as can be seen, it fluctuates day by day. Here we have 7 days, and also fluctuates from different categories. The clothing and shoes are most stable because we have most traffic visits for this category. Okay, here is the conclusion of our work. We propose stock-aware recommender systems with efficient optimization methods. We have successfully deployed the batch algorithm on Tmall.com, and our future work will perform analysis on the online extension and also try to deploy the online algorithm on our platform. Okay, finally, very short advertisement. Currently, we are running a Tianci platform that providing big data with distributed computational resources for academic usage. We have holds a lot of learning and mining competitions, and we are also seeking academic cooperations. Welcome to our booth for more details. Okay, that's all.
Thank you so much, Wenliang. Questions?
Sorry, what do you mean one product?
So when this customer is on this page, so how many products do you recommend?
Oh, okay. Actually, we recommend. Sorry, it's a little bit. Oh, here. We also recommend 3 products based on the value of A.
So is it easy to change this number from 3 to something else, or how does this affect the performance?
I think it's okay to recommend the top K.
Something called assortment optimization in operation research. So it's a classical problem.
Actually, I haven't considered very details as you ask.
And another question, so here S is the stock level, right?
Yeah.
But you assume this stock level is just like completely like exogenous, or it can be determined by Tmall, or so it's like, is this SI like a random, or is also part of the decision variable?
Oh, it's not random. Every day we can.
Wenliang, just repeat the question for the camera.
Oh, okay. Well, this is a great question. There is whether the SI is a random number or determined by Tmall.com. Actually, it's the real number that records by our system that every day we download the table, which is the true number of the stocks, and then we perform the chaining based on this number.
So it's actually changing very quickly during the day, right?
Yes.
You get this number at the beginning of the day, but it may change very quickly.
Yes. Actually, when we performing this optimization, it's also take the change into consideration, as this traffic is the total number of visits for the whole day. I mean, yeah. So it's already take this into consideration. Okay.
Any other questions? Can you speak a bit louder, please?
Yeah.
Let me actually.
The click, flow, and conversion are time-related stuff. How do you consider the seasonality in this function? Do you consider seasonality?
Seasonality?
Seasonality means sometimes you have a high spike during some season. For example, school holiday. For example, like a holiday season, you have a high demand. Do you consider that part in the function?
Yeah, it's a good question. Actually, that's why we perform the chaining day by day, because different season may have different conversion rate and also the traffic. But it's still not good enough. Actually, we found that during the Double 11 day, which is the most biggest promotion day, the performance can drop a little bit, because in this area, in this stage, the estimation is quite noisy. So that's why we propose the online extension of this model.
Sure. For rest of the questions, I would recommend attend the poster session. Thank you so much, Wenliang.
Okay.